-1. And hi, welcome back to Math 234, Multivariable Calculus. So once again, I am still your host, Steve Dragoo, and today we're starting a new chapter. We made it all the way out of chapter 12, which is the chapter that focused specifically on introducing us to vectors, which means finally by the third day of the third week, we're going to do calculus. So, chapter 13 is introducing all of our or at least our basic calculus ideas to vectors. So, it's been a minute since we've done like a derivative or an integral, and that's what's on the docket today. Adding derivatives and integrals into vector functions. Before I get too deep into that, I want to do like 20 seconds of review of what we looked at. Was that yesterday? No, that wasn't yesterday. That was Wednesday. Different classifications of quadratic shapes. A couple of easy ways that I recommend trying to remember what they all are. I've written them out a couple of ways, and you can just vibe with whichever one works better for you. Some of them classified out as paraboloids, the crazy-looking hyperboloids, and then the cone is one way to think about them. Hyperboloids are easy to identify. I don't remember which one I said now. The paraboloids are easy to identify, that's what I want to say, because they've only got a linear term in them. They're the only ones that have a linear term in them. Wow. Whatever. Only ones with a linear term, that's a paraboloid. Linear term with a square term, that looks like a parabola, so they're the paraboloids. You can determine elliptic versus hyperbolic based on the signs of the square terms. If it looks like a circle, it's elliptic. If it looks like not a circle, it's hyperbolic. Then the hyperboloids are where we're going to have the square terms with different signs. So just organize every single term to be positive in a hyperboloid. And if you have one term on the side of the constant number, it's a hyperboloid of one sheet. And if you have two terms on the side of the constant number, then it's a hyperboloid of two sheets. And then finally, the cone is that constant term is 0. So that's one way of organizing your thoughts. The other is the one that I had touched on in class, which is instead to group the hyperboloids of both 1 and 2 sheets and the cone together. And then gather it all up so that all of our variable terms are on one side and the constant term is on the other side. And then I think of the hyperboloids as being either end of a cone. So if the hyperboloid is growing on the outside of a cone, that's going to be a hyperboloid of one sheet. And it grows on the outside because we have a positive constant term that the whole thing is equal to. And if my hyperboloid is growing on the inside of that cone, so if it's stuck on the inside, they've been separated out, so it's now a hyperboloid of two sheets. It'll be separated because there's that negative space through the middle of the shape. And that happens because our constant term is negative, and we end up looking at some cross sections that are circles with a negative square radius, and that doesn't really work so good. So hyperboloid of two sheets, they get pulled apart. Oh, and also as mentioned from that last lesson, the section tends to be more art than science, and it's really just about being able to visualize some of these shapes without needing to spend too much brain power doing that. So we aren't going to do much with actually like transforming those shapes or anything, any hard math with that. It's just about look at an equation, get a very rough idea of what the shape is. That'll help us out. But all right, on to the stuff we're going to do today, which is adding calculus into vectors, specifically vector value functions. So I know I've probably said the phrase vector valued a few times. I can't remember if I've defined it yet or not. So let's just get that out of the way right now. If we say that a function is vector valued, that just means that its output is going to be a vector, or maybe its input will be a vector. Vector valued just means that I'm looking at vectors as a value instead of just scalars or the real numbers as a value. So vector valued just means we're using vectors. So don't get too tripped up by that phrase, I suppose. Or if we're not being pedantic, we'll just call it a vector function. It's probably what we'll do most of the time. And that vector valued function has a domain that is the set of real numbers, and its range is a set of vectors. Or in other words, it takes a real number as an input, like a parameter t, if I'm looking at that line down below, and then its output, just some vectors. So some directed line segment out in space. So a couple of examples of those functions that I blatantly copied from Ryan. There's a line or a helix. And I think even the helix we copied out of the textbook. So here's a slightly better picture of that helix. If I've got a blue cylinder, which I'm using just as my base to create the helix, it is traveling around the surface of that cylinder. So-called helix, or I don't know why it's going to be called a helix, so let me not go deep into that. But instead, looking at its function breakdown, x and y are going to be cosine and sine, which should remind us of a circle, right? Because this helix is traveling basically in a circle, but also if we're adding the z element in, it is traveling up that cylinder. We briefly at least touched on parameterizations, which is going to come up again pretty big in this chapter. But I think most of that we're going to talk about on Monday. But we have a parameterization of that curve listed out as x equals cosine t, y equals sine t, z equals t, or just rewriting x, y, and z in terms of a single parameter, in this case t. If you've completely forgotten about parameters, I would remind you that it is something that came up in Calc 2. So if you've got some old notes from your Calc 2 class, it might be worth reviewing those before Monday's class. Because it'll just help you get a foothold into the other stuff that we're going to do regarding that on Monday. Then we've got the component functions, but I think those are straightforward out of a vector function. The component functions are just the x, y, and z functions, but we can break them down into individual functions, back to like we're used to out of algebra, where it's just, f of t, y of g of t, and h of t, or slightly more conveniently, x of t, y of t, and z of t. So I can label those kind of either way. And there's a bunch of stuff with limits, but I'm gonna gloss over that to instead get to the fun part, where we do calculus. So, the derivative and the integral of a vector function, I think, are just about exactly what you'd expect. If I want to take the derivative of a vector function, which is in turn just three separate functions listed out as components, I just take the derivative of each one right down the line. Since it's a vector function, it should just have a single parameter, which is t going through it. So I don't yet need to worry about mixing variables together, though this is multi-variable calculus, so we are going to be doing that just as soon as we're able to. But for our starting set of derivatives and integrals, we're just going to go back to exactly the derivatives and integrals we've been used to. So just take a derivative right down the line of f, g, and h. Or if I need an integral of my vector function, then it's just the integral of each component right down the line. We, of course, have the super fancy definitions where the derivative is really the limit as h goes to 0 of the difference quotient. I factored the 1 over h out of my vector function, though, because I thought it might be easier to write it out that way. But in each of those individual spots, those are just the standard definition of a derivative. And our Riemann sum version of the integral, where we take the limit of or the infinite limit of a sum, where we're just adding up a bunch of rectangles. Same idea is still going to apply. So, we don't want to focus on those definitions too much. Just know that they're there. if you ever need them. But I think we beat that into ourselves enough in our first take at calculus. So let's just go do the more fun stuff. So considering the function r of t is that function that you can see before us. Let's find r prime. So the derivative of that vector function, r prime of t, is just three derivatives right down the line. Derivative of t cubed is 3t squared. Derivative of sine, I believe, is positive cosine. Cosine t, right? Sine starts by increasing. So it'll have a positive derivative at first. And derivative of e to the 3t, I think, is 3e to the 3t. And probably all of those pieces look pretty familiar. The power rule, the trig derivative rule, and the exponential rule. But again, just we do it 3 times because there's 3 components. That's our problem. Bum, 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 bum. And similar idea, in fact, even the same function. But let's evaluate the integral from 0 to pi of, again, that same vector function. So that's going to look like the integral of each piece. So t cubed integrates to t to the 4th over 4. So I'll be looking at pi to the 4th over 4 minus 0 to the 4th over 4. I'll just call it 0. Then the integral of sine is going to be negative cosine. Right? If I just do the integral of that, it'll go to negative cosine t. And then evaluate at pi and evaluate at 0. Yeah. So what do we have there? Cosine of pi is -1. And -1 is going to become +1. Is that right? I think that's right. And then I go to integrate, or I want to subtract negative cosine of 0. Cosine of 0 is 1, so minus -1 becomes +1. And finally, integrating e to the 3t will become 1 over 3 e to the 3t. And I just need to plug in pi. So 1/3 e to the 3t minus 1/3 e to the 0, which is just 1. So minus a third. Suppose I could clean up the notation slightly. Pi to the 4th over 4, 2, and then 1/3 e to the 3 pi minus 1. I think the last step's a bit optional, though. And when it comes to a whole bunch of those fancy derivative rules, half of which we gloss over and half of which we had to put a ton of effort into remembering, they will still apply to derivatives. So the sum rule, if I take the derivative of 2 vectors added together, I can just take their derivatives first and then sum them. Constant multiple rule is still there. I can just factor a constant multiple out of a derivative for a vector function and then take the derivative. The product rule has 3 different versions. So looking at parts C, D, and E, those are all different versions of the product rule because we have 3 different products to look at. In order, I have the product of a scalar or just regular valued function with a vector valued function. Scalar function vector function, those just multiply straight through. The product and the product rule applies just as you'd expect. I think we're looking at a breakdown of those steps in just a moment. Second version of the product rule is for the dot product. So if I take the dot product of two vectors and want to get the derivative of that, my product rule applies just as it used to. Derivative of one dotted with the original of the other plus the original of the first times the derivative of the other. Hi.
Is U a vector in this? I can't tell.
Gotcha. Yes, U is a vector.
Oh.
U and V are both vectors. And in fact, if I were doing a good job of like reading my definitions, I might have highlighted here. I mean, like that one's on me. So yeah, F is just a real valued function. C is a scalar. But I only have two highlighted colors, so I'm just gonna put those two down. But yeah, I think also if we actually zoom in a bit better, it's easier to tell that those things are bolded. But yeah, so U and V are both vector functions. The third version of the product rule is for the cross product. But again, works just as you would expect. Just make sure that you keep the order in your cross product the correct way. All right, it's got to be U cross V all three times. But then as far as the order of when you do the derivatives, I think that could go either way. Because we do have, the commutative property that says I could reverse the order of addition and it would still be fine. Just make sure that if you're doing the derivative of U cross V, U gets listed first each time in the cross product and V gets listed second each time in the cross product. And then the chain rule is the last one we're looking at. If we're going to take a real valued function, a scalar valued function, and plug it into a vector function, chain rule applies, again, just as we would expect it to. But all right, let's look. Here is a full proof, or a close enough proof, of how the product rule will work for part C, which was the product of a scalar function and a vector function. And you can write it all out, reorganize all your terms, and it comes back to the product rule as you'd expect. So if you're particularly interested, the proof is there. We aren't a proof-based class, though, so we won't be asking for proofs of this kind of stuff on exams or anything crazy like that. Just, I don't know. It feels like we should show you a proof or two because it does sort of apply. But again, we're mostly going to be relying on those things to function in the background. So we can just learn the skills on top of them. If you ever want to learn more, feel free to visit my office hours. And we can talk about proofs all day. Or at least until my office hours are over. Anyway, let's go put some of the stuff into practice. I have found my pen. Never mind. All right, find the derivative of f times u at t equals 1. So for starters, if I just apply the product rule, I know I should be looking at f prime of 1 times u of 1. U of 1. Let's not forget my hat goes on U, but no hat on F because F's a scalar function. Plus, oh no, my pen, it's run out of ink. How on earth an electronic pen runs out of ink? I do not know. But alas, that's what it's done. You would think, oh, maybe the battery is dead. But it's not that. No, my pen just runs out of ink sometimes. I don't really understand it. Science can't explain it. But it's back now. Cool. So let me just erase that scribble and add back in f of 1 times u prime of 1. And again, I'll put my hats on my vectors and I'll not put my hats on my not vectors. So you gets a hat F does not. And we can see that reflected in the values that they are, right? F of 1 and F prime of 1 are just equal to 3 and -4, just equal to numbers, whereas U and U prime of 1 are equal to a vector, 3, 0, -5, and 0, 1, 2, respectively. So that's why U gets the hat. But I digress. This is 3 times the vector 3, 0, -5 plus, I've already made a mistake, 3 times 0, 1, 2. I didn't even need to wait for all the whispering this time. Yeah, that definitely should have been a -4 right there, right? That should have been F prime of 1, which if I look at the given information is very clearly listed as -4. Yep. Great job, me. But I think I got the other parts right. Yeah, they're in the right order. So I'll just simplify my answer a bit. These are two vectors being added together, so I might as well just add them up. -4 times 3 is -12, plus 0 is still -12. Then -4 times 0 is 0, plus 3 times 1 is 3. And lastly, 20 plus 6 is 26. So one thing worth noticing is that if I take the product of a scalar function and a vector function, my result is still a vector. And if I take the derivative of a scalar function with times a vector function, my result will again be a vector. So the forms of our answer won't get changed by the derivative. If I take the derivative of a vector, I still get a vector. If I take the derivative of a scalar valued function, I will still get a scalar as its result. I hear some whispering again, but I don't think there's an error right now. Awesome. Someone told me there's not an error, and I'm going to choose to believe them because that'll make me feel good. But all right, another application of derivatives to vectors and stuff. So if I've got my vector, called my vector function R, and I take its derivative, that R prime vector is going to be the direction or the tangent vector of R. Oh, at A. So this thing has a bit of a mislabel in there. If this thing is the tangent vector at A, I better call it R prime of A instead of R prime of B. Right, I want to plug in A, that value. Make that addition real quick. But if that's the tangent vector, we're going to define the unit tangent vector, usually going to be represented with a capital T, to be this expression. It's just the tangent vector divided by the magnitude of the tangent vector. Anytime I want a unit vector, I just take the vector that I want to have and divide by its magnitude. Unit simply means that it's got a magnitude of 1, and we get to a magnitude of 1 by dividing away whatever magnitude I already have. So unit tangent vector is just r prime of t over its own magnitude. So if I've got a unit or a tangent vector already, r prime of 5, if I want the unit tangent vector, I should just find its magnitude, which looks to me like it's going to be 3. 4 plus 1 plus 4, all inside of a square root. I'm terribly mistaken. That sums to 9, the square root of which is 3. And then for my tangent vector, or unit tangent vector, I already know my tangent vector is 2, 1, 2, but my unit tangent vector is going to be 1 over 3 times 2, 1, 2. I could distribute the 1/3, or I could leave the 1/3 out in front. Either answer is totally acceptable. I think it looks a little cleaner leaving the 3 out in front, or the 1/3 out in front, so I don't think I'll do that. I'll leave it as is. So to actually do the fun part of finding that tangent vector, why don't we start from an original function and then go and figure out its derivative. So hopefully someone remembers the derivative of arctangent, because it's gonna come up in this problem. But first, r prime of t is the derivative of the vector that we had. Just go straight down the line. Derivative of t e to the negative t is going to be e to the negative t plus negative t squared. Oop, stop. Come back, t. So minus t squared e to the negative t. Wait a minute. That's not right. It's just negative t e to the negative t, right? All right, if I take the derivative of e to the negative t, that's just negative e to the t multiplied by the t that's already there. I think I just get that. Cool. So getting past the really difficult derivative, now let's do the derivative of arctangent. So let's see. 1 plus tangent squared is secant squared. So the derivative of arctangent is 1 over 1 plus t squared. If I'm remembering correctly. Got at least one thumbs up from the classroom. So I'm gonna be bold from that and keep moving on. And then 2e to the t, that derivative is 2e to the t. Right, so we've got our derivative. Let's go plug in 0 for t. So r prime of 0 is e to the 0 is 1, minus 0 is still 1. 1 over 1 plus 1 is 1/2. But wait, no, we're not plugging in 1 for t, we're plugging in 0 for t. That's 1 over 1 plus 0, which is 1. There we go. And 2 times e to the 0 is 2 times 1, or just 2. Now that we've got our tangent vector, I'll just go get its magnitude. Magnitude of r prime of 0 is the square root of 1 plus 1 plus 4, or root 6. And for my final trick, at least of this problem, that unit tangent vector, which should just be the tangent vector divided by the magnitude of the tangent vector, is 1 over square root 6 times 1, 1, 2, 1, 1, 2. There we go. Hey.
Has the derivative, it's the derivative. They like has the dash. Then the problem above we didn't put it.
Did we not? All right. Because yeah, the tangent vector should just be. Oh, yeah, you're right. Yep, I see what you're talking about now. Yeah, you're right. That was an extraneous little prime mark right there on the tangent vector. Yeah, tangent vector already has what's called t for tangent, so the derivative is already implied. So yeah, I don't want to take a derivative of it again. Yeah, good point. That would probably be the second derivative, and I don't think we want that yet. It could catch. Cool, yeah. So tangent vector. Ta-da. All right, so antiderivatives, solving an initial value problem. If I've got f prime equal to 2x and f of 1 equal to 3, I should go figure out what f of x is. Well, I know that the integral of 2x dx is x squared plus c. And if f of 1 is 3, that means that f of x is x squared plus 2. To show the work that goes in the middle of jumping from one to the other, that means that I should have 3 equal to x squared plus c, or rather 3 equal to 1 squared plus c. There we go. Right, take my antiderivative with the plus c in it, plug in the point, 1, 3, and I believe I get 2 equals c. Right, so that was our process for figuring out constant values. We want to do basically that exact same thing, but since it's multivariable calculus, we're going to do it multiple times. We're gonna do it 3 times, once for each component. So I've got another initial value problem. I know my derivative or my tangent vector or my tangent vector function. And I know some point that is on the original, on the original function, that original r of t. Combine the two to figure out what our function must be. So on the one hand, I can integrate that whole thing. Let's just call it big R, or regular old R of t. And if I take some integrals right down the line, integral of 2 is going to be 2t. And I'm going to call this plus c1. Integral of the next bit will be 2e to the t plus, how about c2? And you're never going to believe this, but on the third one, I'm going to add c3. But to get there, I first need to integrate the square root function seen before us. So I'm going to get a 1/3 from the chain rule, but in reverse. If I integrate the square root, that's a power of 1/2. It'll go up to the power of 3/2, which means I'm going to need to multiply by 2/3 in order to integrate that thing. And then this is 3t plus 1 to the 3/2 power plus c3. PO. And I've got an initial value problem to solve. Basically, I've got these 3 components. All should be equal to something at 0. And I want to go figure out what that is. So I think if I just leave it on screen barely right there, I can write some stuff down. So 2 times 0 is 0, plus c1 is equal to 4. I'll have 2 times e to the 0, which is 1. So 2 plus c2 is equal to 2. And then I'll get whatever happens when I plug in a number to that square root bit. So let's see. I know that this will be 1/9 or nope, I don't know it'll be that. 2/9, I think is what happens when I combine those constants together. The square root of 0 plus 1, take that back. That's 0 plus 1 to the 3/2, which is 1 to the 3/2, which is just 1. Plus c3, I know that that is equal to 3. So I can figure out what those constants all are. c1 is 4, C2 is 0, and C3 is 3 minus 2 ninths, which is 25 ninths. 27 over 9 minus 2 over 9. Got me to 25 over 9. So now that I know those values, R of t is whatever I get when I add them all up. So 2t plus 4, 2e to the t plus 0, and maybe I'll call this 1 over 9. Nah, I'll leave them separate. 2 ninths times 3t plus 1 to the 3 halves plus 25 divided by 9. Close that down. And my work got a little busy here, so I'm going to put a box around the answer. And go to there, and then go from this stuff over to here. Ah, crap. Go from this stuff over to there. Maybe later. Cool. So we got ourselves a new function. And since that was fun enough the first time, let's do it again. Oh, yeah, that is the last problem. So solve another initial value problem. So R of t, where R of t is gonna be something. I want to integrate each of those things right down the line. Maybe zoom in just a little bit. And then redraw my Langle bracket because I don't like it that much. If I want to integrate 5 over t, I believe that's going to be 5 times the natural log of t. Then I want to integrate 2t e to the t, which is going to be 2 times a thing. I think this is something. That integrates like t squared e to the t minus e to the t. Not quite, right? So let me go back and do this thing again. I know that this is the result of some product rule. So if I were to do that, it would be t e to the t. I know this thing has a derivative. I've seen it before. Oh, let's just integrate it by parts. Fine. So if I want to do an integration by parts on getting my pencil back to having some ink. Ba-ba-bum. Integral of t e to the t. I want to call u t dv e to the t dt. Don't forget your dt, you dummy. Over here, that's going to make dv, I'll slide it that way. That's going to mean that v is e to the t, and du is dt. So that integration by parts should be t e to the t minus the integral of e to the t times dt, which is just t e to the t minus 1. All right, yeah, that was, nope, minus e to the t. There we go. Or written another way, that's t minus 1 e to the t. So this bit over here, 2 times t minus 1 e to the t. We got close. And we just did this derivative earlier. If I want the integral of 1 over t squared plus 1, that's arctangent of t. So let's say you wrote out an initial value problem and you realized somewhere in the middle or possibly just at the end that you forgot about all of your plus c's in the middle there. Because this is an initial value problem, so we have to figure out what our constant values are. Forgot to write all of them in when I was doing this part of the work. An easy way to fix that is to just add the vector c to the end. Let me say this is plus some c vector. C being the vector, C1, C2, C3. So it's a constant being added onto each of those. Pro tip. Just so you don't have to erase all your work to add that back in. Now, the real question is, did I forget while I was writing the problem out, or did I just want to emphasize that? So I deliberately didn't write them in. The world may never know. So we've got some constants to find. So this time we're going to plug in 1 for t. So we'll be looking at 5 times the natural log of 1, which is 0, plus c1 equals 4. I'll have 2 times 1 minus 1 times e to the 1, which is going to be 0, but I suppose I'll write it out. T times 1 minus 1 times e to the 1 plus c2. That's got to be equal to 2. And that last one, I want the arctan of 1 plus c3 equal to 3. And we want to go solve each of these. C1 looks pretty straightforward. It's got to be 4. Since that bit is 0, right? Natural log of 1 is indeed 0. Yep. For the next part through, that's 0 plus C2 equals 2. So C2 is equal to 2. For C3, we'll just need to remember some stuff about the arctangent function. So you recall some stuff about how those inverse trig functions work. That arctangent of 1 part is effectively asking us at what angle is tangent equal to 1. So think back to your unit circle, tangent's y over x. So I want the angle, there we go, from your perspective. I want the angle where y and x are equal to each other, which happens at 45 degrees or pi over 4 radians. And we'll just sort of assume that unless we're doing a word problem, all of our angles are in radians. In particular, when we start applying calculus to the trig functions, we really want those trig functions to be in radians. Because if we want to work with them in degrees, there actually needs to be a change of variable function that gets plugged into those trig functions to switch from radians to degrees. So if we're doing calculus with any trig function, best assume that we're in radians. And then if we want to convert that to degrees for some sort of a word problem, we can do that. But for the calculus part, much easier to be in radians. It's like doing physics in the metric system versus doing physics in the imperial system. One is way easier than the other. But anyway, all I was really trying to say was that arctangent of 1 is pi over 4. So C3 must be 3 minus pi over 4. So I can come back down, write in my final form of the function. It is the vector 5 ln of t plus 4 2 times t minus 1 e to the t plus 2 and arctan tan of t plus 3 minus pi over 4. Zoom back out to try to put all of that on the screen. And there we are. All right, and that was the last problem out of this set. So, unless you guys have any questions you want to talk about, I think we might just end a little early today, since that never happens. Cool. Okay, bye, 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 bye.